Okay, students, we're going to do a pretty thorough review of geometry first semester. This is the updated DCAS sheet that I sent out. This is for the entire year. This would cover between both sides, would cover at least 80% of everything that is being taught and that you know for the DCAS. So if you knew all of this stuff well, you would pass the DCAS at the end of the year. All right, so I'm not going to just go straight through this. I'm going to actually cover more than what's on here between stuff that everything that's on here plus more. Okay. And it's not necessarily in order, but fairly decent amount in order. But here we go. We go to a new page here. There's the back page of that. Okay. So first thing you should know from middle school, triangles add to 180 degrees, quadrilaterals add to 360 degrees, and a circle is 360 degrees. I'm not going to draw that out or write that out. You have it on your DCAS sheet. Let's talk about free undefined terms in geometry, also on there, point, line, and plane. That means that they don't have words to describe those, so we just accept those by what they look like and then use those words from there. The first thing we talked about, a segment. A segment has two endpoints, and you name points, any point, what's an endpoint or vertice, any points are named by capital letters. You cannot use lowercase letters. So that's a segment, and you could write that segment AB. You have to have a segment bar above it. Okay? I'm not going to write out segment AB. If you need to write it out, you can write it out. Next one we had is a ray. And by the way, I can also, if it's a segment, I can go in the reverse order and call it segment BA. Next, we have ray AB. A ray has an endpoint. A is called an endpoint, not a beginning point. We don't have anything in geometry called a beginning point. Okay, A is an endpoint. It goes through B forever. That's why there's an arrow here at the end. Okay, and if you write it as AB, what is above A? A is the endpoint, and it goes through B forever. The other way of writing it, that's the normal way of writing it right there. If I was to write BA, those points in that order, again, A is the endpoint, goes through B forever, so the arrow must go the other direction. Okay, so those mean the same thing, ray AB. And you pronounce it that way. Even this one you pronounce ray AB because you start by naming the endpoint first. Okay, so they're both pronounced ray AB. All right, next we have a line. A line has a segment, ray, line. Any of these have an infinite amount of points on it. If you know that, to be asked that, there's always an infinite amount of points between any 2 points. A line could have, again, many points on it. I'm just going to use 3. There's multiple ways of naming lines. I can pick any 2. I never use 3 letters on a line. I use any 2. I can call it line AB. Again, I have to have arrows on it because the line has arrows on it. It goes on forever. I can call it BC. I could call it CA. Those are just 3. Any combination, any order for that. Now, another way a line is named is if I have a lowercase letter at the end, even though the line never ends, where one of the arrows is. It's not anywhere in between. It would be at one of these ends. Obviously, I can't have 2 different letters. So I'm just showing you it could be on the right end, N, or it could be at the left end, P. It's going to be one or the other, not both. Okay, so that's also line N. Okay, next we have a angle with a common endpoint. There, let's call it ABC. Okay, this is an angle. An angle, by definition, if I look at, I have a ray BC and a ray BA, right? Those are two rays that we just talked about. Two rays make up an angle, and they must share a common endpoint. This common endpoint is B. So that's the definition of an angle. Two rays that share a common endpoint. Now, that's also close to the definition of a line. If I have two rays that happen to be opposite rays, so let's go ahead and that's ray BA, and this is ray BC. If they're opposite rays, so that's the definition of opposite rays, rays that go in the exact opposite directions with a common endpoint, which is B in this case. Those are called opposite rays. Opposite rays form a line. So that's how a line is described, a pair of opposite rays. So that's ray BC and ray BA. Okay, now naming angles. Let's go back to naming angles here. Okay, I can call this is called the vertex angle. So that's the vertex point. So I name a point not in the vertex. So this can be called angle CBA, angle CBA. I could switch the order. This is the angle symbol, by the way, right there. I can call it angle ABC. Since there's only one angle in this drawing itself, I could call it angle B. And lastly, if they put a number there, I could call it by that angle number, angle 4, for example. Now, this is the one that is least used and the one you don't want to use hardly ever. Okay, angle B, because rarely after this very beginning will we ever have a single angle by itself, unless we're talking about, polygons. We're talking about triangles. Each of these is an individual angle. But many of the times in geometry, we're going to have multiple angles around that point, around that vertex. So I cannot call it by a single letter. I will always be using either the 3 letters, or if there's a number there, I could call it by the number. So if you're in doubt, do not use a single letter, use the 3 letters. Or if there's a number there, use a number, okay? If you don't get this down, you're in trouble the rest of the year because you have to name angles constantly. When you get to proofs, you have to name the angles correctly and in corresponding order. So if you can't name them, you're in trouble, okay? All right, next we have markings on a segment for, or anything. Could be a segment. These are called hash marks. The same, if this has one hash mark, this has one hash mark. That means they are congruent. Equal number of hash marks mean congruent segments. Okay, so you have to have that memorized. So if I put another one on there, that means that those are not congruent. They're different lengths. Okay, so know that. All right. I could have it angles as well. So if I drew an angle here and drew another angle here, and I put an arc, these are called arcs. Arcs. So the same number of arcs means those angles are congruent. I'm not going to write that out, so I'm trying to save time here. Same number of arcs mean the angles are congruent. Okay, so if it's segments, you use hash marks. If it's angle measures, you use arcs. So if I put 2 on there, there's 2 of them, there's only 1 over here, that means those 2 angles are not congruent. Okay, now I put the second one on there, now they're back to being congruent. Okay, we start at 1, 2, and work our way up usually. Okay. Okay, next we have parallel lines cut by a transversal. Let's go to the next page here. Parallel lines, you should know from middle school, parallel lines means two lines that never intersect in the coordinate plane. So we have a plane. Speaking of that, we draw a plane, usually what looks like a parallelogram. That's also how we draw a plane. And in a plane, you identify a plane in one of two ways. Plane, by definition, is three non-collinear points. Okay, that's how you name a plane. Three non means not, co means same, and linear, the key word in linear is line. Non means not. So I have to name 3 points that are not on the same line. So could I call this plane ABC? No, I could not, because those points are all on the same line. It's true this line is in the plane, but I cannot name the plane. Okay, a plane is any flat surface that goes on forever. So this board, all the way horizontally and vertically, forever, that's what a plane is. Obviously, you can't draw that either. So this is how we draw it. But when naming a plane, you have to name it by 3 non-collinear points. So I could call it, for example, and we can use, I can write out the word plane, or I can just draw the plane symbol and say plane A, B, D. 2 could be collinear and the third one is off. I could call it plane CBD. Now, if you notice the difference between A, B, C, D, points A, B, C, D, and this letter P down here in the corner. P, does that have a point by it? No, it does not. So you cannot call and use that point because that's not a point. So when I say non-collinear points, they actually have to be physical points in the plane. Okay? So 3 non-collinear. You hear the word collinear? Because you might be asked in an assignment, name 3 collinear points. That means 3 points on the same line. Non-collinear means 3 points not on the same line. 2 can be on the same line, third one off. Okay? The second way of naming a plane is by the capital letter. Can't be a lowercase letter. Capital letter in one of the corners. So this could also be called plane P. Okay? So that's the way you name a plane, just so you know. All right, so back to over here now. Parallel lines. So the way we identify parallel lines now for the next symbol, if they don't tell you in words in the direction of the parallel lines, we draw arrows like this. Sometimes they're filled in like this, just so you know. Other times they're just drawn like that, somewhere on the line itself. That means parallel. That means these 2 lines are parallel. Again, if I had a third line, even if it looks parallel, it's not unless I have the arrow on there. Okay, and again, the same number of arrows means those lines are parallel. So I could have 2 lines here, and they could be parallel, and they put 2 on there. That means they aren't parallel to these blue ones up here. Okay, because they only have 1 arrow on them. So again, the same number of parallel arrows shows you those lines are parallel. All right, so there's my parallel lines. A line that cuts through both of them is called a transversal. Okay. So this drawing would be called parallel lines cut by a transversal. That's how you describe that. And we have, if I go ahead and name numbers now for these angles, because that's the quickest way of identifying an angle is with numbers. We have different types of angles here that you have to memorize. Okay. We're going to go through all the pairings here. Okay, so I'm going to go ahead and erase all this so I can draw it over here, write it over here, I meant. Okay, we have the 4 common ones that we always think about with parallel lines cut by transversal are AIA, stands for alternate interior angles. A-L-T for alternate. I-N-T, I'll just write out alternate interior. That's the angle symbol, plural for angles, alternate interior angles. Okay, now alternate. When I think alternate, just think diagonal, across from one another, diagonal across. Interior means inside. So you think inside what? Inside the parallel lines. So those four angles that are inside the parallel lines are 3, 4, 5, and 6. So that means those are the only four you can choose from whenever you have the word interior. And obviously the last A is angles. Okay, so it tells me I'm choosing between 3, 4, 5, and 6 because they're interior angles and they have to be alternate. So that means they have to be diagonal from one another. So that'd be that pairing and that pairing right there. They're diagonal. So alternate interior angles would be 3 and 6 is one pair and 4 and 5 is the other pair. Now, there's nothing else to explain on that. You either choose to memorize that or you choose not to. Don't say, I don't get it. There's nothing to get. You memorize what these angles are. It's as simple as that. So if you have to make flashcards, you do this. You have to do that with all the angles. That's just the first pairing. We're going to go through all the different pairings here. It's the same idea. These are all perfectly explained right here. You either choose to memorize it or you choose not to, and you get blown all throughout the year. Okay, next type we can use is alternate exterior angles. Alternate again means diagonal. Exterior means outside. Outside of what? Outside of the parallel lines. So, what are the four angles that are outside the parallel lines? 1, 2, 7, and 8. Those are the only four you can choose from. Again, alternate means diagonal. So which ones are alternate? 1 and 8. What's the other pairing? 2 and 7. Very simple. You know what alternate means, you know what exterior means. You know what alternate means, you know what interior means. Okay, nothing to it. Elementary kids can easily do this. Okay. All right. Next, let's talk about what do we know about their angle measures. All alternate interior angles are congruent. This is the congruent symbol. Okay, means congruent. Okay, what does congruent mean? Simply, same size and shape. Means, I'll just put equals. Equals, same size and shape. Okay. So it's talking about the actual drawing of the angle itself. Now within that, since the drawing of the angle is exactly the same, then the measures are going to be the same. So a lot of people like to say the angles are equal in measure, which they are. So anytime the angles are congruent, the angle measures themselves are equal in measure. So what's the difference between saying congruent and just saying the word equals? And when I use the word equal, talking about the angles, I'd say the measure of angle 3 is equal to the measure of angle 6. Okay, that would mean that the number, we're talking about a number of degrees, like 40 degrees equals 40 degrees. So it's a number. So when I use the equal sign, I'm talking about numbers. Some number equaling another number. Okay, I'm not talking about an angle. If I want to talk about the angle itself, I must use the congruent symbol. That's the difference. Even though all congruent angles also have equal measures by definition, if I'm talking about the angle itself, I use a congruent symbol. If I'm talking about the measure of the angles, and little m stands for measure, obviously it's the angle symbol I've already described, then the equal sign is used to identify numbers. So I'm going to have a number on each side there. Okay. All right. So alternate interior angles are congruent. Alternate exterior angles are also congruent. Okay. So I'm going to go through the three congruent ones first. The next type is corresponding. Corresponding is usually the hardest for students to remember. Again, it's just straight memorization. There's nothing to understand. You either memorize or you don't. Just like a Spanish vocab word. You either memorize or you don't. Okay. All right. So corresponding angles. Our pairings for those are 1 and 5 is one pair. 3 and 7 is another pair. 2 and 6. Oops. 2 and 6 is another pair, and the fourth pair is 4 and 8. Okay, so now how can I see? I have 1 and 5, 3 and 7, 2 and 6, 4 and 8. What you'll notice on all these pairings, one angle is an exterior angle. For example, in 1 and 5. 1 and 5, which one's the exterior angle? 1 is. 5 is the interior angle. Okay? So you have to have one interior angle, one exterior angle, and they cannot be adjacent to one another. Adjacent means next to. So the adjacent angle in the interior to angle 1 is angle 3. Those are adjacent angles next to one another. Angles 1 and 2 are adjacent as well, but both those angles are exterior. Remember, I told you that one angle is interior and one angle is exterior. So 1 and 3 cannot be it. Even though that's an angle interior and angle exterior, they are adjacent next to one another. They cannot be. Corresponding, you have one adjacent, one outside exterior angle, one inside. And you can, if it's drawn like this, you can just think that you're skipping the angle 3 and going on to the next one. So the other characteristic is they're on the same side of the transversal. Notice they are not alternate. None of these are alternate. None of these are diagonal across the transversal. They're on the same side of the transversal. You got to know that. So 1 and 5 are on the same side, 3 and 7 are on the same side. 2 and 6 are on the right side of the transversal, 4 and 8 are on the right side of the transversal. One's an exterior, one's an interior, and they are not adjacent. Okay? Know that. All right, so what's true about all corresponding angles? They are also all congruent, meaning they're equal in measure as well. Okay? In our last type, let me move this down. We have, I guess I can't move down that far. Same side interior, SSI, same side interior. Okay, also called consecutive interior. Consecutive means one after the other. INT for interior. I'm not going to write it out. Same side interior, that would mean same side of the transversal. And they're interior angles. So again, my only 4 interior angles here are 3, 4, 5, and 6. Those are the only ones I can choose from. What are on the same side of the transversal? Remember, the green is the transversal. The same side would be 3 and 5. So that's one pair, 3 and 5. The other pair that's on the same side as each other and inside or interior angles are 4 and 6. Now, what is true about 3 and 5 and 4 and 6? They are supplementary. They are supplementary. Okay, so now we need to go ahead and break down that word. Supplementary means, by definition, two angles that add to 180 degrees. Okay? Supplementary is the vocab word. You gotta have that memorized. Two angles that add to 180 degrees. Now, here's a common wrong way students say it. Two angles that equal 180. No. If I say in English, two angles equal 180, that means each angle equals 180 degrees. We're trying to learn the English language here. Okay? Two angles that add, or you say sum. The sum of two angles is 180 degrees, because sum means the answer to an addition problem. I always just say two angles that add to 180 degrees. That's the definition of supplementary. Now, let's go, so those are the 4 main types we have right there. Okay, I'm going to redraw this on the next page and just use that same drawing, or I'll just go like this right here. We'll just do this. Okay, so if I call angle 1, 2, 3, and 4, okay, angle 1 plus angle 2. Okay, so first off, angles 1 and 2 are, let's just say angles, oops, angles 1 and 2 are adjacent. Remember what adjacent means. I've already described it. Adjacent, I'm just saying, instead of writing the word means, I'm just saying equals. Next to. Anytime I say what's adjacent mean next to, that means they're connected. They share the common ray. Okay, so angles 1 and 2 are connected. They're right next to each other. Angles 1 and 3 are adjacent. Angles 3 and 4 are adjacent. Angles 2 and 4 are adjacent. Those are all adjacent angles. They're next to one another. Now, so that's adjacent. Next vocab word is vertical angles. Again, this is straight memorization. There's nothing to understand. You either memorize or you don't. So if you have to write out flashcards to do it, you do it. Vertical angles are across from one another, diagonal. So angles 1 and 4 are vertical angles. 1 and 4. And angles 2 and 3 are vertical angles. 2 and 3. So notice in vertical angles, they will form opposite rays. There'll be two lines. Okay, so to see that, there's one line. We'll make the other line green. There's a second line. They could be full out segments that would, if I extended the segment, would be lines or rays that would turn into lines. Okay, but they're going to be two lines formed, and it's the diagonals right across from one another. The diagonal angles right across from one another are called vertical angles. What's true about vertical angles? You should be able to tell me already because I put arcs on them. We already talked about arcs. Arcs mean equal measure. So that means angle 1 is equal to angle 4. The measure of angle 1 equals the measure of angle 4. The measure of angle 2 equals the measure of angle 3. Okay? Vertical angles. Next, another pairing that we have in here, when we have, next vocab word is linear pair. What's the key word in linear? Line. Do we see a line here? Yes, we do. So a linear pair, by definition, are two adjacent angles that create a line. Okay? Adjacent means next to, and they must create a line. Both of these, so angles 1 and 2 create a line, angles 1 and 3 create a line, angles 3 and 4 create a line, and angles 2 and 4 create a line. All those are linear pairs. So 1 and 2 is one, 1 and 3 is another, 2 and 4 is another, and the last would be 3 and 4. Those are all linear pairs. Again, if you have to memorize it, do it. All right. Linear pairs are always, what do angles 1 and 2 add up to, do you think? Those angle measures. In other words, what's the angle measure of a line? 180 degrees. So all linear pairs, what's the word when we have two angles that add to 180 degrees? You just had it down on the last page. Supplementary. So all linear pairs are supplementary. Okay? And supplementary means two angles that add to 180 degrees. Now, to go along with that, notice I said two angles. You can't just say angles that add to 180, because if I say angles, that could be 2, 3, 4, 5, or 6, however many I want that add to 180. No, two angles only. So, is that a linear pair? Because it creates a line. There's a line right there. There's a line. So are angles 1, 2, and 3, do they form a linear pair? No, they do not. Why? Because what's the word pair mean? Two. Only two. That's 3. So that is not a linear pair. Pair can only be 2. It must form a line, create a line to add, therefore, to 180 degrees. Now, do angles 1 plus 2 plus 3 add to 180? Yes, they do. So I can say measure of angle 1 plus 2 plus 3 adds 180 because it creates a line, and all lines are 180 degrees, but that is not a linear pair because it's more than two angles. All right, so I think I've covered anything dealing with that and all of our major angle measures that you have to have memorized. Then that we'll use forward from here. Okay. Let's go to the next page here. All right. Now, remember, we started with parallel lines cut by a transversal. Remember, they identified parallel lines like this. So I knew that they were parallel. Then those four types of angles, alternate interior angles, alternate exterior angles, corresponding angles, they're all congruent, and the same side interior angles are supplementary. That's guaranteed if they're parallel lines. Okay, well, what if they're not parallel lines? They're just two lines that may look like they're parallel. Just because they look like they're parallel or not parallel, we don't go by looks. They have to have markings on them or in words in the directions. Okay, but we want to prove that they're parallel. So we're going to talk about proofs. Dealing with this right now. Okay, so if I want to prove that lines N and P, remember I can name lines with a little lowercase letter at the end, so we'll call these lines N and P, and we'll call this L. L being the transversal. I want to prove N and P are congruent. The only way I can do that is if I can show that one of those four types of pairings, either alternate interior angles are equal. So if I can show that equals that, then those two lines are parallel. Or if I can show this angle is congruent to this angle, the other alternate interior angle pairing is congruent, then those two lines are parallel. Or if I could show corresponding angles were congruent. So I can show those two red ones are congruent. They're corresponding angles. If the corresponding angles are congruent, then the two lines are parallel. So what is my justification? Also called a reason nowadays. Justification and reason mean the same thing in proof. We talk about proofs later. Okay, justification equals reason. Now they changed it because so many kids didn't understand what justification meant, so they made it simpler. What's the reason to be able to say that? So if I'm going to now say, if I can show that these two corresponding angles, and so for example, if I had 2x minus 4 and I had 4x minus 16. Okay, well, if I want to show that those two angles, those two lines are parallel, then these two angles must be congruent. So I would set those two angles equal to each other to make them congruent. So I'm going to subtract that across, add that across, and I get 2x equals 12. And I get x equals 6. So if x equals 6, then those two lines N and P are parallel, because then those two angles are congruent. Now, what's my justification of showing that? It would be converse of, and in this case, corresponding angles postulate. POST for postulate. Okay, a postulate is an accepted statement of fact. Okay, like sort of like common sense. We just accept it. Versus a theorem is something that has to be proven. So notice this is called a corresponding angles postulate. An axiom or postulate is not proven. Okay, not proven. They're accepted statements of fact. Okay, so instead, accepted statements of fact. Okay, it's like common sense. Okay, that's for axiom or postulate. A theorem must be proven. So sometimes these are on the GCAS. Axiom or postulate would be a multi-choice answer. They'd have one or the others. They'd say, and they'd have different vocab words in there to say which one of these below is an accepted statement of fact, and which, if whether axiom or postulate is in there, that's the one you choose. If they're both in there, you choose both of them. It would be that'd be a multiple answer one. Okay, theorem must be proven. Right. So converse of, we start with whenever we are trying to prove lines parallel, and that's on your DCAS sheet. Okay. When trying to prove lines parallel, that's the parallel symbol. Two segments, vertical segments. Okay, so I'm not gonna write out the word parallel at all. That's the parallel symbol. So you're learning the vocab. It should be reviewed, but if you want to watch at the beginning of the year and learn this stuff, now you're learning it right now. That's the parallel symbol. That's the only, whenever I have converse of, and in the DCAS, they may not have converse of at the beginning, but it'll have the words converse in there. Okay, that's only used in justification when you're trying to prove lines parallel. That means we don't know they're parallel to begin with, trying to prove it. So I could prove it through corresponding angles postulate, meaning I show corresponding angles congruent. It could be through the alternate interior angles theorem. So that one's a theorem. It could be through the alternate exterior angles theorem, or it could be through SSI, also called consecutive interior angles theorem. Okay. So I could have shown any of these pairings. So SSI, they'd have to add to 180, right? The two consecutive interior angles would have to add to 180. Okay. So that would be showing this green plus that green would add to 180. If I can show that, solve for that and show that, then the two lines N and P are parallel. So it could be any one of these four along with the word in front of it, converse of. That would be our justification and proof of why those two lines are parallel. All right, that's that one. And that's talked about on there. Okay. We're not going to talk about constructions because I'm told that they're being taken off the DCAS. Okay, let's talk about exterior angle theorem. I'm now doing all shortcuts. EXT for exterior, there's my angle symbol, and TH for theorem. Okay, so you start learning shortcuts here and writing things in geometry. Exterior angle theorem. Exterior angle, exterior, we already talked about it with parallel lines. That means outside. So be outside the triangle. So if I have 1, 2 angles, 1, 2, 3, and 4, the exterior angle is 1. Okay. Now, the measure of angle 1 equals the measure of angle 3 plus the measure of angle 4. Angle 3 and 4, these two angles, in relation to angle 1, have two possible wordings for them. I don't have room to write it there. I'm going to write it down here. They can be the two opposite interior angles or two remote interior angles. Okay. So what this would say, the measure of angle 1, or the exterior angle, if I want to use just words, I could say the exterior angle of a triangle equals the sum of the two opposite interior angles, or I could say the exterior angle of a triangle equals the sum of the two remote interior angles. Remember, sum, addition, answer to an addition problem. That's how you describe it in words. So in the DCAS, in final or etc. tests, they might either have just numbers in there or they have algebraic expressions in there. So very simply, if I had something like this and they said x 3x plus 9, so they said this was x plus 2 and this was 2x plus no, this would be, dang it. Okay, right there, x plus 7. No, let's go x plus 5. Okay, so that would say my equation would be 3x plus 9 equals x plus 2. That's the one angle plus x plus 5, the other angle. So I combine like terms, I get 2x plus 7 equals 3x plus 9. Subtract the 2x across, I get 1x. This is not good. I should have changed this and made, let's make this I made up numbers without, dang it, made up numbers without looking very well. Let's say this is 3x minus 9. Okay, so I change this to a minus 9 right here. So I'm going to add a minus 9 right there. Okay, so now I have x. I add the 9 across. 9 plus 7 is 16. Okay, so the answer, if it asks for just for x to be 16, if it asks for one of the angles, I'd plug the 16 back in. 3 times 16 is 48. Minus 9 is 39 degrees. Of course, not going to be the case realistically because that's an obtuse angle greater than 90 degrees, but from what it looks like at least. Okay, but anyway, that's how you'd set up your equation. Okay. So since I just used the word obtuse, let's go ahead and throw that in there real quick. Obtuse, this is stuff you just know from elementary school and middle school, is greater than 90 degrees and less than 180. Acute, x is greater than 0, less than 90. Right angle, also called perpendicular, equals 90 degrees, exactly. And you can have a 0 angle, which then is 0, and you have a straight angle, which is a line, which we already talked about, equals 180 degrees. Okay. Side note on the difference on how you name a 0 angle. Let's call that B and this A. So a 0 angle here would be, for example, 0 angle would be, for example, angle CBC. It goes in and comes right back out. Or I could use from the other side, angle ABA. Versus straight angle goes straight across to the other side. That would be angle ABC or angle CBA. Okay, make sure again they're all capital letters, no lowercase. All right, so there's your main types of angles right there. So I just spoke about angles. Quick review. Okay. Let's go to the next thing here. Triangle sum theorem. I should have stopped at TH. Triangle sum theorem says all 3 angles of a triangle add to 180. Okay, and so that's a justification in a proof. If you're showing that 3 angles are adding to 180, justification is triangle sum theorem. So that's also under, and so you could have a triangle and have algebraic expressions, you know, x plus 4, 2x minus 7, and say 3x minus 1. And so I would add all 3 of those angles up, set them equal to 180 degrees, solve for x. Okay, and I can plug it back in to get the angle measures. That'd be the triangle sum theorem. Okay. Let's go to the next. Isosceles triangles. Definition. DEF always stands for definition. At least 2 congruent sides. Notice I didn't say exactly 2 congruent sides, at least 2 congruent sides. So, what's the triangle that's got 3 congruent sides called? Equilateral. Equa meaning equal, and lateral means side. Okay, if you didn't know, lateral means side. Equa is the same as equal, so equal sides. Equilateral, all 3 sides are congruent. Okay? So therefore, an equilateral triangle is also isosceles. Because it says at least two, which means two or three. So all equilateral triangles are isosceles, but isosceles are not equilateral. It doesn't have to be three, it could be two. All right, so remember, that would be an equilateral for sure. And this should be an isosceles one, two congruent sides. This angle, or angles are always mentioned by capital letters. This angle A is called the vertex angle. Vertex angle is where the two congruent sides, remember we know they're congruent because they have two hash marks each, come together. It's at A. That's called the vertex angle. The side opposite the vertex angle is called the base. So therefore, these two right here are called base angles. I'm just going to draw it both right here, base angles. Okay, because they're on the base. Now, if I have an isosceles triangle, that's the definition of isosceles triangle. It's based off of the sides, at least two congruent sides. If I have an isosceles triangle, then I can say automatically, by a theorem I'm going to say in just a second, that the base angles are congruent. So I put one arc and one arc. Okay, that is called the isosceles triangle theorem. Okay, base angles congruent of an isosceles triangle. Okay, so isosceles triangle theorem. So I can automatically have that on all isosceles triangles. Now, next, if I draw a segment from the A down to the base, from the vertex to the base, and make it at a right angle, also called perpendicular, which obviously means it's on the other side as well. Okay, that segment is called the altitude or the height. Altitude equals the height. So oftentimes you'll see it with an H there for height. Okay. Now, let's talk about, so in the altitude of an isosceles triangle, don't forget, that'd be the same on equilateral because all equilateral triangles are isosceles. So all these same rules apply. But now, if I think about this, if that's my two congruent sides, these are my two base angles. And if these are my two congruent sides, then these are my base angles. So all angles of a triangle, of an equilateral triangle, are the same. And what do all angles of a triangle add up to? 180. So what's 180 divided by 3? 60 degrees for each angle in an equilateral triangle. Okay. And obviously all the sides are the same. So if that was 4x, then this has to be 4x, and this has to be 4x. So what would be the perimeter of that triangle? 12x. 4x was 4x was 4x is 12x. That'd be the perimeter. Okay, now back over here, this altitude from the, and we'll call this point D, from A to D, that's the altitude, because it goes from the vertex to the perpendicular, the opposite side. That's called the altitude or the height. That is also, so that altitude is called a perpendicular, and it's also a bisector. So it bisects the base. So I put a hash mark on each side there. This is true of all isosceles triangles, which would then also be true of all equilateral triangles. Equilaterals, isosceles. Okay, you're guaranteed to have two of these questions on the DCAS. Okay, and maybe two on your semester exam as well. Okay, because there's so much information here. Now, we're going to talk about ways of proving triangles congruent, and then come back to this page. I'll do this on the next page, and then show it on here with the isosceles triangle. Okay, so we have 5 ways of proving triangles congruent. Remember, that's the congruent symbol, equal sign with a little similar bar above it. Okay, 5 ways. SSS stands for side. Anytime it's an S, that equals side. Anytime you see the capital A, that represents angle. So that means side, 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 angle, side, angle, 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 side, and HL theorem, which stands for hypotenuse leg. Now you should know from middle school, the only type of triangle that has a hypotenuse and a leg on it is in a right triangle. So only in right triangles. Okay. So I'm just going to draw one of each. That's what a side would look like. If I had SAS, side, angle, side, and these could all be different. Okay, just so you know that. I'll put the other one. So if I have another triangle down here, okay, it'd have to have 1, 2, and 3 also. Okay, this would just be a rotated one, but as long as they have 3 of the same side lengths, 3 of the side lengths, so I could have 2, 3, 4, then this would have to be a 2, a 3, and a 4. Okay, I could have numbers on them as well. So since I have 3 side lengths of the same length in each triangle, that'd be an SSS. Okay, side angle side. This A has to be right between the two sides, where the two sides come together. It has to be that angle. That is called the included. The one that's in the middle, included, is the vocab word you see described in words on the decals, and just think of that meaning in between. So that angle is in between the two sides, but the vocab word that you'll see in the geometry is included. Okay, SAS right there. Okay, ASA, angle, side, angle. So in that case, the S is the included side. If you say 2 angles and an included side, will be the definition of angle, side, angle. Okay. AAS, angle, angle, side. AAS. That was ASA. Okay, now angle, angle, side is the trickiest one because, as I'll show you in just a second, it depends on which side that S is on. Notice this S right here is next to the 2 arcs. So here be one that you might think, you might say, oh, those 2 triangles are congruent because I see AAS in this one and I see AAS in this one, angle, angle, side. But here's the difference. These are not congruent. So if I put a congruent symbol, you put a not through it. They're not congruent because this side is next to the one with 2 angles, 2 arcs. So that's a different angle measure compared to this side is next to the one with 1 arc on it. It's a different angle measure. So those 2 are not congruent. Okay. The side itself on the S has to be next to the same number of arcs in both triangles with the same degree measure. You know, if this was 40 and this was 40, okay, then that'd be next to 2. I'd have 2 there. But it's got to be the same angle measure, okay? This side has to be next to the same angle measure, same number of arcs, okay? And lastly, HL, remember that has to be a right triangle. So there's a right angle, there's my hypotenuse in one of these 2 legs. Doesn't matter which leg. So you have a hypotenuse. Remember, the hypotenuse is always the longest side. It's always across from the 90-degree angle every time. It's the longest side of the right triangle. That's the hypotenuse. And these are called legs, if you forgot. So each one's a leg. I just put plural, but each one is a leg. So it doesn't matter which leg is congruent with the hypotenuse. It just has a hypotenuse in one of the legs. Okay. So now let's go back to this isosceles triangle here. And I look at these 2 triangles. And I have multiple ways that I can show these 2 triangles, if I call it triangle 1 and triangle 2, that these 2 triangles are congruent. Okay, one other justification, another justification that's on your sheet there to prove triangles congruent is if I have a side congruent to itself. Any side I can name it congruent to itself, and that is called the reflexive property. Reflexive property, P-R-O-P-T, of congruence. And I could have just said REF for reflexive prop of in the congruent symbol. If I ever say a side is congruent to itself or an angle is congruent to itself, that justification or the reason is reflexive property of congruence. Okay, and we use that in proving triangles congruent when we actually do a proof. Okay, that's one of the free points you can get is reflexive property. So now I know that's true because that segment is in both triangles, that same one. So it's in both of them, so it's reflexive property. All right, so now if I look, I have SSS. There's an S and an S and an S, 1, 2, and 3, 1, 2, and 3. So it's proven by SSS. Those two triangles are congruent. I could use ASA, ASA with the right angle symbol. Okay, on both of them, ASA. So I could use ASA. I could use AAS. There'd be A, S, A, S. Remember, because the S is next to the one with the single arc on both of them. I could use SAS. I have, I'll go with black for SAS. SAS, SAS. Okay, every one of these works. And HL works because it's a right triangle. So I have my hypotenuse and I have both legs. I only need one leg. I have a hypotenuse in both legs, so I always have SSS. So in an isosceles triangle, you can prove them congruent on all the ways possible. Now, what does it mean to be congruent? It means the exact same size and shape. So all the corresponding angles have to be the same angle measure. So we already see that we have one arc and one arc here for angles C and B. They have to be congruent. We already have the right angles are congruent. They're both 90 degrees. And once I prove triangles congruent, I can say any other of the other parts that aren't marked within the triangle. So in a triangle, we have 3 sides and 3 angles, right? We have all 3 sides already marked in this particular one, and we have 2 of the angles, but we don't have the third angle marked. So I can put 2 arcs right there and 2 arcs right there. Now that I've proven 2 triangles congruent. Now my justification for that in a proof would be what's called CPCTC. That's on your justifications there, CPCTC, and that stands for corresponding parts of congruent triangles are congruent. So notice it says corresponding parts of congruent triangles. That means I already proved the triangle's congruent. We just showed all 4 ways, 5 ways. Most of the time it's only one way you're going to prove it congruent, but in a isosceles triangle you can use all 5. Okay, that's why it's special, isosceles triangle. So corresponding parts. What corresponding part means is segment AC matches up with AB, segment CD matches up with BD, and segment AD would match up with segment AD. Okay, and the angles. Angle 1 matches up with angle C with B. The right angle, so angle CDA with angle BDA, and the top angles on the vertex up there, angle CAD and angle BAD, are congruent. Okay, those are called corresponding angles. They match up the same angle measure in the other triangle. That's called corresponding. So we have 3 corresponding angles and 3 corresponding sides. So we would say that there's 6 corresponding parts in all triangles. Okay. In quadrilateral, since there's 4 sides and 4 angles, there'd be 8 corresponding parts, 4 sides and 4 angles. If it was a pentagon, 10 parts, 5 sides and 5 angles. Okay, that you'd match up if they were congruent. Okay. So that's more vocabulary. CPCTC is only used after proving triangles congruent. Only used after proving triangles congruent. That's to be the last step. Okay, I have to go through my steps first. Prove the triangle is congruent by one of those 5 ways that we just did. This would be the step, one of these steps, one of these ways of proving the triangle is congruent would be the step before using CPCTC. Okay, So know that. For some reason, students, when we get to the proofs, they think they can put CPCTC before. Obviously, they don't listen. They aren't paying attention. They aren't taking notes right in class. Okay, and or using the notes and memorizing their notes. CPCTC can only be used after proving triangles congruent by one of these 5 ways: SSS, SAS, ASA, AAS, or HL. That has to be before the step before using CPCTC. Okay. All right. Next we have segment addition postulate. So if I have A, B, C, and I'm just going to put numbers in. They could be algebraic expressions, they usually are, in order to make you use algebra skills. If I say that length is 2 and that length is 3, okay, then the length, or so notice when I write AC here, do you see anything written above AC? I'm not including the circle because I'm just circling that. No. When there's nothing above it, AC itself, that means the distance from A to C. Okay, so you have to know that. That's the one that's the trickiest one because there's no symbol above it. And again, the kids who don't study, don't use the correct vocabulary in class, and just try writing down answers. They're the ones who also don't know their vocabulary. They struggle all year long in geometry. I'll warn them at the beginning of class. It still doesn't matter for them because they aren't caring to get a good grade, meaning A, B, or C. They're satisfied with a D or F. That's what it means if you're choosing not to learn all this vocabulary. You're choosing to get a D or F. Okay, they're the ones who aren't going to be able to tell me that AC means the distance from A to C because they don't study, they don't volunteer in class. Same kids who don't volunteer answers in class, who don't participate in class. Okay, it's always the A and B students who are constantly answering all the questions because they want to participate, they want to get their good grade in class. They do what good students do. Okay, and that's why they get their grades. They've done it all along for years. So if you want to stop being a bad student or a weak student, then start doing what A and B students do. You've got a long ways to catch up because you haven't done it for probably your math career. Okay, you got to change your attitude if you want to become a good student, at least in math. All right, so just from A to C would be 2 plus 3, which equals 5. So when I add 2 segments together, obviously AB is a segment AB plus segment BC equals segment AC. That is called the segment addition postulate. And that should be common sense because, and that's why it's called a postulate, because it's common sense. Remember, it's something that doesn't need to be proven because it's common sense. Because I took 2 segments, AB and BC, and I add them together. So segment addition postulate. Now, like I said, on the test, it would have algebraic expressions. It might have 2x plus 3, and this one might have 4x minus 1, and then it might tell you that the whole length from A to C was 40. And so I would add those 2 algebraic expressions together, set it equal to 40, and solve for x. And then if that was the answer, if they said solve for x, you're done. If they say what's the length of AB, you plug the x back into segment AB. If they want the segment length of BC, you plug the x back into BC, the 4x minus 1, and give the answer. Okay? So that's the segment addition postulate. To go along with that, there's an angle addition postulate. The exact same thing. Again, that's why it's called a postulate, because it's common sense. For those of you who have common sense. Okay, some of you don't. I take 2 angles, 2 adjacent angles, and add them together. So again, in order to be an angle, I have to have points here. Okay, so if I take angle, and I'll just go ahead and name it angle 1 and 2, so I don't have to call it by all 3 letters. It'd be ABD plus CBD. So I can say the measure of angle ABD plus the measure of angle CBD equals the measure of angle ABC. These two angles added together equal the entire angle, angle ABC. That's common sense. That's why it's a postulate. So that's called the angle addition postulate. Again, they will put in algebraic expressions right in here. For those of you who don't still know what algebraic expressions are because you didn't study your vocab and all through middle school in Algebra 1, whenever you hear the word algebraic, that means it's going to have a variable in it. Algebraic has variable in the expression. So common variable we obviously use is x that you see most of the time. It doesn't matter what the variable is. So whenever you see algebraic, that guarantees you it has a variable in it. And an expression, the simplest way to think of an expression means doesn't have an equal sign. Okay. The one that has the equal sign is called an equation. So it has equal sign. Okay. So if I have 2x minus 1 equals 5x plus 2y plus 3. So let's just review quick algebraic vocabulary one time. You've had this told to you for years already, starting in 6th grade. So if you're a 10th grader, it's 6th, 7th, 8th, 9th. This is your 5th year of hearing this. If you're a 9th grader, it's the 4th year of you hearing it. Okay? The good students are the ones that have this stuff down because they've been studying. So this is an equation because it has an equal sign. This side of the equation is called an expression. This side of the equal sign is called an expression. Again, they don't have equal signs. So the definition of an equation would be an expression that equals another expression. Okay? Now, within an expression, you have terms. So here we have two terms. Terms are separated by plus and minus signs. Plus or minus sign. Okay, so I have two terms there, 2x and negative 1. This side I have three terms. I have 5x, I have 2y, and I have positive 3. Three terms. So an expression is made up of one or more terms. An equation is two expressions equal to each other. Know that. You're supposed to have known that for years now. That's the only time we're going to sit there and go over this. Okay. So, let's see. If you look at your DCAS, I'm just going to go over a couple of things on the main justifications. We already talked about given is always what you write down first in a two-column proof. Two-column, so proof. I'm just showing you the general setup. Proof, you're trying to prove something. The left side are called statements. The right side, reasons, and I always call them justifications, as you've heard, but they've broken it down to simple word for reasons. Okay, just so you know, the very first thing you write down in all proofs are the givens. Okay, they'll have the givens up here, and you write them down. You just write them down, copy exactly as they are. You don't change anything, any wording, anything like that, any order of letters. You copy down exactly it is. Then you have your steps in the proof. Okay, your justifications in the proof. Okay, so when it says main justifications, that's the same thing as saying main reasons. Okay, I wrote down justifications on your DCAS sheet. You can add in the word reason if you need to next to it. Okay, the reasons are the same thing as the justifications. The last step is what you're trying to prove. Copy what you are trying to prove. Okay, if you're trying to prove triangles congruent, then this last step over here would be one of those 5 ways of proving triangles congruent, like I was saying. SSS, SAS, ASA, AAS, or HL. One of those 5 ways. If the question was to prove triangles congruent, and that's what you're mostly going to do in our proof section, or you did if this is a review for you at the end of the semester. Okay, but remember, there could be one more step after the proof. Okay, so if it's going beyond the proving the triangles congruent, we're going one step after that. Then this would be the next to the last step, and then the last step would be what? I already wrote it down for you prior. CPCTC. Okay, so that could be the last step. It's usually one of those two. We're keeping it that simple. Okay, if it says prove triangle such and such is congruent to triangle such and such, then this is your last step, one of those 5. If it says prove this side is congruent to this side, then this will be your second to last step, and your CPC TC would be your last step, saying that that side was congruent to that side after proving the 2 triangles congruent by one of these 5 ways. Okay, so that's your general setup of a 2-column proof. Your justifications in there. If they have a vocab word up in the given, you're going to use the definition of that vocab word. Okay, and we'll talk about that. I'm not going through all the different vocab words now in this review, but one of your justifications would be definition of vocab word, whatever that vocab word is. Okay, so that's also one. Now, common ones for sure that you almost are always using is reflexive property of congruence. Okay, when that's again when a side equals a side, so segment AB is congruent to segment AB, for example, or if an angle equaled itself, angle A is congruent to angle A. When you talk about overlapping triangles, for example, you'd have an angle congruent to itself. Okay, so what's an overlapping triangle? I'm just going to quickly draw it one for you. Overlapping triangles. Right there. A, B, C, D, and E. So triangle ABD is the smaller one, and that is overlapped by triangle ACE. Those are called overlapping triangles. So angle A is in both triangles, isn't it? So if I was talking about using this angle for some reason, we would not be proving these 2 triangles congruent because one's obviously bigger than the other. Congruent means same size and same shape. But another example of overlapping triangles that you could see in a proof would be like this. And you'd be talking about this triangle right there being congruent to this triangle right here. Okay, and then this angle, if we call it angle A, is in both triangles. That's one where you say angle A is congruent to itself, reflexive property. Okay, so that's where the angle would be congruent to itself with reflexive property. We saw it with the isosceles triangle theorem where we had the side congruent to itself in the isosceles triangle, this congruent to itself. Okay, that'd be an example of that when the sides are in both triangles. Okay. All right. Next, let's go ahead and talk about, I'm going to do transformations last. Okay. So let's go ahead and talk about mid-segment. Even though mid-segment could be in quarter 2. Where do I have mid-segment? I put it in quarter 1. Okay, mod 1. All right, so let's go to mid-segment here. mid-segment? Obviously, it means the middle of a segment. Common sense. Okay, we have two shapes, two common shapes that we use mid-segments with. Use with triangles and trapezoids. It's usually isosceles trapezoids, but it doesn't have to be. Okay, so I'm just going to do one of each. There's a triangle, ABC. If I take 2 points in the middle, are those the, and we call them D and E, is that, by just looking at that right there, is that the mid-segment? No, you cannot say that because remember, we go by the identification marks. Now, if it said in the problem, DE is the mid-segment in words up above in the problem, yes, then it's a mid-segment. So you always go by wording there. But if not, I need to see hash marks. Oops. See hash marks on it showing it's a mid-segment. Now D is called the midpoint. Now the vocab word. D is the midpoint of AB. If I see this here, then E is the midpoint of AC then. Middle point of a segment. Because D is a point and E is a point. So midpoint versus segment. Now that I have that those are midpoints, now segment DE is called a mid-segment because again, it's a segment. It's not a point as D and E are, it's a segment. So it should be common sense. We call it the mid-segment. So now what are the two characteristics of a mid-segment? Two characteristics. CHAR for characteristics. DE, or I'll just say mid-segment is parallel to the base. Okay, or for the trapezoid, base is. Okay, when I draw, if I draw, you know, isosceles trapezoid, or it didn't have to be, I was going to draw isosceles. Let's draw a regular trapezoid. Okay, equal, 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 equal. Connect them. So now it's a mid-segment. A, B, oh, we'll make it the same. We'll call it D and E on this one as well. A, B, C, D there. So DE, it's parallel. So we can write or draw the parallel symbol on it. That's one characteristic. The second characteristic is, so that's, two characteristics. Number one, mid-segment's parallel to the base, or base is, because there's two bases here. Oops, I got to put the other parallel symbol there. And two, mid-segment equals 1/2 the sum of the bases. Now, the reason I'm saying that, because in a trapezoid, you got two bases, right? AB is a base. AB equals a base. Segment AB is a base. And segment CD is a base. Okay, so I would add those two together. Let's say this is 10 and this is 17. I'll make it 18, so it's a nice, easy number to divide by for the rest of you. 10 plus 18 is 28. Divided by 2 is 14 then. Okay, the average or the half the sum of the bases, or you can say the average of the bases. If what's average mean, add the numbers together and divide by how many there are. Well, there's only two bases, so add them together and divide by 2. That means the average. Or you can say half the sum of the bases. Well, if I think of the bases on a triangle, I really only have one base, but if I want to call A a base, that distance is 0, isn't it? So I can still say the sum of the quote bases, even though A is not a base. A is called the vertex. Okay, but if you want to think of that, so you have the exact same definition, A's base should be 0 in length, and so you're just 0 plus BC divided by 2. So it's just half of BC. Okay, so if this is 2x, then this has to be half of that, 1x. That's simple. So there you have it in algebraic expression form, and here I did example with numbers. Okay, so that's mid-segments for either trapezoid or triangle. All right, next. Side splitting theorem. Side splitting theorem. I have, for example, 3 or more parallel lines cut by 2 transversals. Okay. Then what side splitting? So these transversals would be considered the sides. Okay. Splitting. They're splitting the parallel lines. Okay. So these sides, each segment will be a piece of a side. Okay. They are proportional. So let's say this is 3 and this is 6. And if I say this is 4, and that's x, what does x have to equal? Well, very simply, I can write it vertically. 3 over 6 equals 4 over x. Notice I'm matching up the corresponding sides. 3 matches up with 6, so they're on the left side, top over the bottom one. And so I have to go top over the bottom one on the right side, 4 over x. That means corresponding order. And of course, I could reduce 3 over 6 down to 1 over 2 equals 4 over x. And now I could cross multiply and I get x equals 8. So x has to be 8. 3 over 6 is the same ratio as 4 over 8, 1/2. Another way I could have set it up, I could have set it up 3 over 4 equals 6 over x. Notice in that way, if I wrote it that way, that's the same proportion. I'm going across. I just went left to right on the top one, so I have to go left to right on the bottom. I could have gone right to left. I said 4 over 3 equals x over 6, as long as I go in the same direction. Okay, so now, how do I can either cross multiply, or here's one of the shortcuts I've shown you. 3 times what is 6? 2. So then I have to multiply by 2 here. 4 times 2 is what? 8. There's my answer, 8. Exact same answer. Okay. Notice if I cross multiplied right away, I have 3x equals 24. 3x equals 24. That shows that those are the exact same proportions, just written in a different format. Those are the 2 common ways. Doing it either vertically on top of each other or horizontally, side splitting theorem. Okay. Next, we have the angle bisector theorem. So this is in a triangle, and it bisects an angle. Notice I have one arc and one arc. That means it's bisected. That angle is bisected. So this is the angle bisector. That segment itself right there is called the angle bisector. Bisect means what? Bi means 2 sections. It splits it into 2. Okay, so 2 congruent parts. 2 congruent angles right here. If I have that situation, then let's say this is 10 and this is 5. I say this is 20 and this is x. Okay, then I write my proportion, because this all goes under the concept of similarity. Okay, by keeping my proportion on the same side of that bisector. So I can write it as 10 over 5. So I went sort of like, if you want to think of this as a hypotenuse, or the longer side over the shorter, like that. This side corresponds with this side. So since I did 10 on this side on the numerator, I must do the 20 on the numerator on the other side, because that's the corresponding side. And then x corresponds with the 5. These two correspond. Okay, remember I got to write them in corresponding order. And now I go ahead and solve it. I can say 10 times what is 20? 2. So 5 times 2 is 10. The answer is 10. So x would be 10. That's as simple as you can get it. Now, of course, they're going to probably have algebraic expressions for you. I'm just doing it real simple here in numbers. But you set up the same proportion. Whatever this algebraic expression is right here, over this one equals this one over this one. And then you could cross multiply and solve the equation. Now, the tricky one, just so you know, if you had something like that, the trickier one of it, if I had that angle bisector, of course, now I know it's an angle bisector, so it has the markings there showing they're congruent. Now it's an angle bisector. And let's say they tell me this was 10, and this was X, and this was 20, and this was 30, okay? And they say solve, let me put letters in here, A, B, C, D. Okay, notice again, all capital letters because all points are capital letters, never lowercase. We'll use lowercase for side lengths that we'll talk about in a little bit, and then also on naming lines, again, if there's a lowercase letter at the end of a line next to the arrow there, that's where you see lowercase also. All right, so if they want to say find AB, or if I say AB, that means the length from A to B. So notice I'm like, oh boy, what do I do now? Well, I can still fill this in with some algebraic expressions, because if this is X and the whole thing, so let's just say I call that Y, because I don't know what it is. It's not X, it doesn't have to be X. That means it's the exact same length. It doesn't have to be, so we're going to call it Y. I know X plus Y equals 20, don't I? It's the whole length. Well, so if I want to rewrite Y in terms of X, solve for Y, and that'd be 20 minus X when I subtract that across. So I can now rewrite this as 20 minus X, because I want to write it in the same algebraic, same variable. Okay, so X plus 20 minus X, what does that equal? Doesn't it equal 20 because the X's cancel out? And there's my 20. Okay, so now I can set up that proportion as, let's move this over here. I would have it as 30 over 20 minus X equals 10 over X. Well, 10 times what is 30? 3. That means I multiply by 3 here. What's 3 times X? 3X. So that means this has to equal 3X. So now I have my equation. So I'm just writing it over here. 3X equals 20 minus X. Move the X at the same sign, so add the X across. 4X equals 20. Divide by 4, and I get X equals 5. So the answer is 5. So that'll be 5 right here. And 20 minus 5 is 15. And doesn't the ratio of 10 over 5 equal 2? And doesn't the ratio of 30 over 15 equal 2? So I know I'm right. I can easily plug it back in. So that's called the angle bisector theorem. Okay. Okay, what do I want to do next here? Since we're still doing triangles, let's go with triangle inequality. Triangle inequality theorem, okay? Any two sides of a triangle must, I should say, not any two sides, the sum of any two sides. Got to say it correctly. English matters. Sum of any two sides of a triangle must be greater than the third side. Okay. So example, if I have the lengths, so question, triangle, can this be a triangle? 2, 4, 7. Can those three side lengths be the sides of a triangle? Well, all I have to do is take the two smallest. Does 2 plus 4, is that greater than 7? Because remember, the sum of any two. So I always take the smallest two every time. The tallest, smallest two must be longer, the sum of the smallest two, that is, must be longer than the longest side. Is 2 plus 4 greater than 7? No, it's not. So this is not a triangle. It means it can't create a triangle. You can't connect the side lengths to make it a triangle. Okay. So speaking of that, real quick, the definition of a polygon. So if I have, here's a side length of 2. Here's a side length of, say, 4. Double that. This right here would be my 7. Okay. And you might say, oh, that's a triangle. No, it's not. Okay. Because the definition of a triangle is a polygon. So a triangle, a quadrilateral, 4 sides, 5 sides, pentagon, hexagon, septagon, octagon, nonagon, decagon, 11gon, or undecagon, and dodecagon for 12-sided is dodecagon. Those are all polygons. And we're talking about convex polygons. Convex polygons is the only thing we work with. Convex polygon, very simply, is versus non-convex. Okay, so let me draw non-convex so you see. We can't do anything with non-convex because there's just no rules that hardly apply to it. We need, if we're going to do math, we got to have certain rules that are always going to work. So here would be an example of a non-convex polygon. Okay, it's all sides, it's all segments. So a polygon is made up of only segments, not curves. So a circle is not a polygon. All segments. Okay, but here's how I know if it's convex versus non-convex. Non-convex, if I extend any of the sides, they will not go inside the polygon. Well, that extended goes inside. That one extended. It only has to have one that goes inside. If one goes inside, it's non-convex. We don't deal with those. So when I say we only deal with convex polygons, a triangle would be a convex polygon. That's a true triangle right there. Okay, because if I extend any of these sides, they do not go inside the triangle. So that's called a convex polygon, just so you know, vocab-wise. All right, so the definition of a polygon is that the segments, the 3 segments, that's 2, 4, and 7, polygon definition is all segments must come together at endpoints only. In a plane. In a plane is a flat surface. Okay, so it's not 3-dimensional. Okay, so notice this segment, there's the endpoints. It's too long. That 7 is too long. That's why 2, 4, and 7 don't work. That 2 and 4, there's no way I can make it stretch out that 2 and 4, because even if I made it the 2 here and made the 4 as long as possible for a line, that's only a total of 6. And the other segment is 7. It's longer. So there's no way I can connect those, so they only intersect at the endpoints. Okay? They must come together only at their endpoints. This is not an endpoint, that's not an endpoint, so it's not a triangle. Okay, so now you've learned definition of polygon as well. Okay, and non-convex versus convex. We only deal with convex polygons, and that's all the formulas we have. Okay, so let's go ahead and go on to this. So you could have a question, and you will have a question. You have it if it's a review. Name all possible side lengths, all possible lengths of the third side of a triangle. Given the first two. Or given 2. Okay, so if I tell you, I give you one side length is 4, another is 9. What are the possible side lengths of the third side. Very simply, x, the third side, you put inequality symbols there, you have to remember to put those there. So x is greater than, and this answer comes from subtracting the 2. 9 minus 4 is 5. And this one comes the greater, the maximum is going to be less than, is adding the 2. 9 plus 4, 13. So the third side length must be between 5 and 13. That's your answer. Okay? So that's called the triangle inequality. So I showed you to see if they gave me 3 sides, I just add the 2 smaller, it has to be greater than the third. If it's not, notice I said greater than, not greater than or equal to. So if I have 2, 3, and 5, that also is not a triangle. It has to be greater than. That's 2 plus 3 equals 5. It has to be greater than 5. Okay, so just notice that. But if they give me 2 sides and they ask me to find the possible lengths of the third side, that's where I have to do this one right here. Okay. All right, that's triangle inequality. Let's talk about, still with triangles, ordering. If I say that's 12, that's 13, and that's 14. A, B, C. Okay, and it says order angle measures from smallest to greatest. Okay, this angle 13, I mean, the side length 13 was created by the opposite angle, B. So angle B maps up with angle 13. Angle C maps up with 12. Angle A maps up with 14. You just memorize this. Okay, so which is the longest side? 14 is. So that means this must be angle A is the greatest or longest. Okay, which is the shortest? 12 is the shortest. That maps up with C. So C equals the shortest. And then therefore B is the middle. So it says to go ahead and go from smallest to greatest. So it'd be angle C, angle B, angle A. That'd be your answer. Okay. Now to go along with that is I could go backwards if they were giving me the angle measures instead of the side lengths. So say this was 40, this was 50, and let's say make them bigger because I gotta be add to 180. So let's say 70, 65, that's 135, that'll be 45, 180. And we call this C, B, A. Okay. Well, this angle 70 is the largest. If we're going smallest to greatest, here's the smallest angle. So that makes this the smallest side. So side is segment AC. We're going to talk about another way to name these in just a second. The next smallest is angle C, so that's then segment AB. And obviously this is the greatest, so that's the longest, segment BC. Now, talk about naming sides. Another way to name sides, besides the 2 letters for the segment itself, is if they give me, it's in a triangle, it's in a polygon like this, capital B, opposite is lowercase b, because they correspond together. Capital A, this makes this lowercase a. Capital C, this makes this lowercase c. So this is the only other time you're using lowercase letters in naming things. Side lengths, and then the end of a line, as we already talked about. If I have a line, they could call it lowercase p right there, and not show you any points on the line. If they had points on the line, A and B, call it line AB, line BA, or line P. That's a lowercase p, not capital. All right, so if I did it by side lengths, it'd be by the single letter, that's letter B, that's letter C, and that's letter A. So that'd be another way if you had it numbered or lettered like that. Lowercase b, lowercase c, lowercase a. So now you know you can also name sides like this. Okay. Okay, rigid motions. Time to get to it here to finish off mod 1. Okay. All right. We have what's called transformations. It's a major concept. It's on the DCAS. Okay. Now I have, this is a quick overall review. We know it's going to be over 2 hours, but this is for the whole semester. So getting it done in just over 2 hours is pretty doggone good. I obviously have not covered everything in detail. Obviously, I've got videos for every one of these concepts that would take a lot longer than this. If you add them all up, it'd be many, many hours. Okay, I'm trying to give you all the general ideas again. Okay, so some of you, if you watch at the beginning of the semester, you could pick up on, if you're smart and have good memory, you could learn a lot of what you should learn the whole first semester right here. Okay, or get a lot of it down and have general ideas beforehand. If you're watching this for the first time at the end of the semester, then this review should be plenty good enough because you should already know the more detailed stuff already. So I should just have to go over the general ideas. Okay, so transformations. We have what's called rigid motions, or also called isometries. You got to know that they're called the same thing. They mean the same thing. And then we have dilations. Okay. Underneath rigid motions or isometries, you have a single reflection. So I'm just writing the number of reflections on the side there. That's 1. You have 2 reflections. If it's over parallel lines, it's called a translation. Okay, over parallel lines. Okay, I also have 2 reflections over intersecting lines, and that's called a rotation. And lastly, I have 3 reflections, which is called a glide reflection. And that is a translation, then single reflection. Okay, and that should make sense. Because a translation has 2 reflections and a single reflection has 1. And what's 2 plus 1? 3. Okay, so that's what a glide reflection is. Now the DCAS focuses on these first 3. Okay, but just in case they throw it on there, they may or may not call it glide reflection. They would just, since a translation and a reflection all fall in the first 2, I mean the first 3 words here. That's why they may not use the word glide reflection. Okay. Now, these are all congruent. This is the definition of congruence. DCAS's definition of congruence. Definition congruent. Going from the pre-image to the image, and I'll break down those words here in a second, by any combination of rigid motions. Of course, or they could say or isometries, since they're the same thing. So you want to memorize this definition. Guaranteed you will have that definition on the DCAS. they will ask you to explain in a box. They'll say, why do you know that these two pre-images and image, these two triangles, these two quadrilaterals are congruent? Your answer is because I can go from the pre-image to the image by a combination of rigid motions. There you go, right there. There's your definition. That's why how you explain that they are congruent from pre-image to image. Now, pre-image means before. This is the first one, first drawing, and the image is the last. And it's usually only the second, but it could be more than the second, but it's the last one. Okay, if there could be ones in between. Okay, and technically you can call any of the ones in between an image as well. Okay, and I'll draw an example of this coming up here of these, so you see this. Okay, with our rotations, singular function, all this, I'll do an example of the first three. Okay, and what you need to memorize in regards to. All right, dilation, as we talked about, these are similar. Okay, so what's the definition of similar? Definition, same shape, but not necessarily the same size. Okay, now 99.9% of the time they're not going to be the same size, but they technically, by definition, can be the same size. So dilation with a scale factor of 1, that means it's the exact same, 1-to-1 ratio. So it's congruent. So congruence does fall underneath dilations, but they usually will keep them separate out here. Okay. So if it's the same shape, all angles must be congruent. All corresponding angles, that is. CORR for corresponding angles are congruent. So if one shape has angles of 30, 40, and 50, the other shape must also have angles of 30, 40, and 50. The difference will be the side lengths. The side lengths will either be bigger or smaller. Okay. If it gets bigger, so underneath here, bigger, for the pre-image to the image, that's called an enlargement. It's all vocabulary you need to memorize. If it gets smaller, so the pre-image, and then it goes smaller, that's called a reduction. Okay. And so then their side lengths will be either larger or smaller, but it's got to be by the same ratio every time. Okay. Also, what's true within these dilations is if there's parallel lines, they remain parallel. All the corresponding lines remain parallel to one another from the pre-image to the image. So it's called parallelism. So not only do angle measures remain the same, but the side lengths are proportional, the same ratio for each one, and the corresponding sides are parallel to one another. Okay, for all of that. Okay, so that example was our overlapping triangle. When I had this and this, and then this would be called the center of dilation. When I call that angle A up there, that'd be the center of dilation. I dilated this pre-image, let's say that was a small one, and I dilated it from the center A and went out, and now I created this larger triangle. Okay, that's dilation and enlargement specifically. Okay, so if we say enlargement, it doesn't mean the figure got bigger, it means it's also a similar figure. Okay, enlargement, reduction, similar figure, but smaller. Okay. All right, so now let's go ahead and look at, oh, okay. I'll go to the next page. Within reflections, each single reflection switches orientation. So now you ask, what is orientation? Orientation is either clockwise or counterclockwise. So clockwise, sometimes let's just say C, or counterclockwise. I call that CC. So example, so every time you do a reflection, when I say each single reflection, that means it doesn't have to only be one reflection. Every time you do a reflection, one reflection, two reflections, every time you reflect over, it switches orientation back and forth, one time each. So if I sit there and drew this triangle ABC, I reflect it over the y-axis. That means it goes at a 90-degree angle and the same distance away. So that has to be equal to that. So that is now called A prime. The ones without, so this is called a prime. Okay, vocab word. This doesn't have the preimage. This is called the preimage. This is how I know which one's the preimage versus the image. Preimage, no primes. Okay, there's no primes on them. The image has primes on them. The C would come to right here because it's the same distance away, so that's C prime. And the B would come over here, same distance away. And I reconnect them, reconnect those. And that's B prime and that's C prime. Okay, so now I talk about the orientation. If I go ABC, notice that is counterclockwise. But on this single reflection over this ABC is now clockwise. So notice it switched orientation from counterclockwise in the preimage to clockwise in the image. That's what it means of switching orientation for every single one. And then if I go ahead and reflect it over the x-axis now, take this one, reflect over the x-axis, that goes there, that goes there, that goes there. So now this is A double prime. This is B double prime is how you pronounce it, and C double prime. Okay, because so that would tell me, here's my preimage. Since this has a single hash marks, primes on them, that means that is the first reflection. And these ones have double primes, that means this was the second reflection, the second image. Okay, now if I look at ABC here, we're back to counterclockwise. So I went from counterclockwise to clockwise on the first reflection, and from counterclockwise or clockwise back to counterclockwise for the second reflection. Every time you do a reflection, it switches orientation. Okay. So you want to check from the preimage to the image, you want to check their orientation. Check orientation from preimage to image. And when I say image, I'm going to say that means the last one. Okay, so this was the first, this was the second, and this was the third. So I'm comparing 1 and 3, the first and the last. Check orientation from the preimage to the image. Okay, final image, if you want to call it, because there could be more than one. Like the second one there, we have 3, and 1, 2, and 3. Okay, so in this one, I'd be checking 1 and 3. Notice the orientation is counterclockwise and counterclockwise. So did it switch orientation from the beginning to the end? No, it did not. Well, if we go back to here, when I have 2 reflections right here, this is the same orientation. Okay, if I have an odd number of reflections, this switches orientation. So odd number is 1 or 3. Switches orientation when I compare first to the last. So if it switched orientation between 1 and 3, it would tell me I had either a single reflection, there's only one of them, or there was 3 of them, and it would be a glide reflection. But since this one right here kept the same, counterclockwise, counterclockwise, that means that this had to be a translation or a rotation. That was the only 2 options. Now we go back and look at which one it is. The definition of translation is 2 reflections over parallel lines. A rotation is 2 reflections over intersecting lines. So you go back and look in here. It first got reflected over the y-axis, then the x-axis. Are those intersecting lines? Yes, they are. So this is called a rotation. Okay, I was able to get, by checking the orientation first, I was able to get down to 2 of the 4. This is the value of checking the orientation first. I can get down to 2 out of the 4. Okay, so since orientation did not change from first to last, it had to be a rotation or a translation. And now I just look at the 2 lines. They intersect, so that's the definition of a rotation. If they're over parallel lines, so I went from here to here to here, okay, 1, 2, and 3, then that's a translation. A translation is like a slide. All I do is slide it. So the shape hasn't rotated at all. It stays exactly the same. It just slid. Okay, that's called a translation. That's over parallel lines. Okay, so that's the value of you checking its orientation, or if they just happen to ask you, they might ask you what the orientation is. Okay, I might ask you, or they could ask you on the DCAS, so you need to know that. Okay, let's see here. Okay. All right, centroid. We're only going to talk about the centroid because that's the only one of the 3. I'll think about it here. That is on the DCAS. Okay, so centroid. A, B, C. And triangle again. Try to keep the triangle stuff together here first before I go on. I'll go back. Since I'm here, I'm going to do it now. I'll go back to drawing with reflections and rotations and things you have to memorize with the rotations piece, or even reflections piece as well. And translation. We'll do examples of each. Just a second. I should have done it. I'll just do it now. I'll erase this and do it now. So keep it in order. Oh, what this happened there? Okay. All right. So I'm just going to show you by 1 point alone. Okay. You do this for all 3 points in a triangle or in a quadrilateral. Okay. That point is 2, 1. You got to be able to name points from elementary school. If I reflect that over the y-axis, that's right here. I go 2, so I got to go 2 over here. It's got to be at a 90-degree angle to the line that you're reflecting over in the same distance away. So this point is now negative 2, 1. So if I reflect over the y-axis, my original point of x comma y became what over here? That became negative x comma y. The y did not change, but the x became the opposite sign. So this is the rule. Negative x comma y. If I reflect, little r stands for reflection. Okay, just so you know. And this subscript tells me what it's being reflected over. Okay, so the y-axis. Sometimes they'll just write reflection of y. If it says y, that means the y-axis. They'll either write out y-axis or just y. Same thing. If I go over the x-axis, I'll just write it as x. Okay, I take that same point, reflect over the x-axis. That puts it right there. What is that point? To negative 1. Okay, did the x switch? No, it didn't. So it stays as x. The y is what became the opposite. So the rule for reflection over the x-axis is xy becomes x negative y. These you need to memorize, or you just draw out like this and figure it out yourself. Okay, the next one I can have is if I reflect it over the line y equals x, the most famous line in math. That's at a 45-degree angle. Okay, just so you know that. When I reflect it over there, that's 2, 1 comes on to right there. It's 90 degrees, the same distance away, and that point is 1, 2. So reflection over the y equals x line of my original point. XY is always just the original point. in this case 2, 1, it became 1, 2. What happened? 2, 1 became 1, 2. What happened? It switched the y and the x. So that's the rule for reflection over the line y equals x. Okay. I can also reflect over the line y equals negative x. Y equals negative x. Okay, don't forget the y-axis, that equation is x equals 0. The x-axis, that equation is y equals 0. You just know that from Algebra 1. But of course, many people in geometry, when I quizzed them on this, did not know this still. Okay, it's pre-algebra in Algebra 1. You're supposed to know this, right? Equations of horizontal and vertical lines. Okay, so I've done that one. Now I have reflection over the line y equals negative x of my original point x comma y. What does that become now? Okay, now here's how. So I can memorize all these. I can just draw them out like I'm doing right here and come up with it. Okay, you can do the same thing. If you don't want to memorize it, you just know how to draw them out. Okay, and come up with yourself. But a lot of people, it's simpler for them just to memorize these things. Okay, I just visualize it in my head and come up with it and just recalculate it out each time. Okay, so if you're having difficulty, pick one that's right near it. So negative 2, 1, and that reflects right there to negative 1, 2. Okay, so negative 2, 1 is my original. What happened? This x became the y. Oops, comma. The x became the y, and it switched the sign. That negative 2 became positive 2. This original y became the x, and it took its negative. I said it wrong. Okay, I explained it, but I didn't write it right. Hold on. So I'm looking at the new point. That new point, what is the negative 1? Negative 1 is related to the y coordinate of the original, but it's the opposite. This y coordinate of the image is related to the x coordinate of the original, but it's its opposite. That's how you need to say it. So reflection over the line y equals negative x of xy becomes negative y negative x. That's its rule. So that's for our main reflections right there. Now, if I had a reflection over another line, for example, if I took and reflected over, this is y equals negative 1. Okay, that line right there. If I took this point right here, negative 3, negative 3, and reflected over line y equals negative 1, I have to go at 90 degrees straight up in the same distance. That distance is 2, so I must go up 2. Right there. Okay, so it becomes negative 3, 1. Oops, positive 1. Okay, so there is no rule when it's over other lines than these major 4 right here. Okay, if it's over another horizontal or vertical line other than these, you just have to count. It's always going to be at 90 degrees to the line in the same distance away. So if it's 2 here, I'm going up 2. 2 over here. So it's a reflection. Okay, so that's how you do it with horizontal or vertical. You actually have lines outside of these right here. You have to count them yourself. Don't forget the y-axis is also called the line x equals 0. So it might say x equals 0. The x-axis is also called the line y equals 0. So they might say reflection of the line y equals 0. So that they see if you know what that equation is, that it's the x-axis. Okay, so that's just a side note right there. Okay, so that's with reflections. Now let's go ahead and look at rotations. Okay, I'm going to again just do it with a point to make it faster. Okay, you can do it with each point. So let's say I take the point 3, 1. Okay, capital R stands for rotation. So I do a rotation of 90 degrees. So you have to know your quadrants in the degrees. This is 0 degrees always. This up here is 90, 180, 270, and back up to 360. So positive degrees is counterclockwise. I'm adding, okay, so positive degrees, counterclockwise. Positive degrees, counterclockwise. Negative degrees, clockwise. Okay. So if I want to go negative, I'd be going this direction. That's negative degrees. So rotation of 90 degrees is from here, 90 degrees this way. So I'm starting here, and this always means about the origin. Okay. If they don't say it's about some other point, which most of the time it's not on the DCAS, they may give one at most that's not on the origin. And I'll do a quick example of that. Even though we're at 2 hours and 6 minutes right now. All right, so rotation of 90 degrees. Okay, this is quadrant 1. Knowing your quadrants, quadrant 2. So let's know this from algebra 1, quadrant 3, quadrant 4, written in Roman numerals. Okay, the reason they're written in it's those quadrants in that order is because that's how the degrees go. 0 up to 90, that's the first set. 90 to 180 is the second set, quadrant 2. 180 to 270, that's the third set. And 270 to 360, the fourth set. That's how those quadrants got their names. Your teachers in middle school might not have told you that, or algebra 1. They might have just told you to memorize it. So explain it to you. Now you know why, and you can explain it to anybody else. Okay, so rotation. Every quadrant is 90 degrees. So if I start in quadrant 1, as I am as 3-1 is, and I'm going 90 degrees positive, which is counterclockwise, I must end up in quadrant 2. If I start in quadrant 2, I must end up in quadrant 3. If I start in quadrant 3, I must end up in quadrant 4. That's positive 90 degrees counterclockwise. If it said rotation of negative 90 degrees, and I start in quadrant 1, I must end up in quadrant 4, because clockwise is negative degrees. If I start in quadrant 4, I must end up in quadrant 3. If I start in quadrant 3, I must end up in quadrant 2. If I start in quadrant 2, I must end up in quadrant 1. So just knowing that, you'll know where your final point, quadrant it should be in. Okay, so I know I better get an answer in quadrant 2 since I started in quadrant 1. So here's the rule, and so this is what I visually do in my head because I memorized the rule, not the rule, but what's the two reflections. Remember, rotation is two reflections over intersecting lines. I memorized what those two intersecting lines are and visualize reflecting over them instead of just memorizing the rule itself. So a reflection of 90 degrees is a reflection over the line y equals x following that little circle O in the middle like that means following a reflection over the x-axis. Okay, so that means following. This is function notation. You did function notation in algebra 1 where it's written as like f of x equals such as 2x plus 1. That's function notation. Well, in terms of transformations, this is considered function notation. Right there, doing something like that. Okay, all right. So what's the rule for reflection over? So that means I go right to left every time. So I do the reflection over the x-axis first, reflection of the line y equals x second. That's my order, right to left. Remember that because you'll do this in algebra 2. You'll see that in algebra 2 also with equations. You go right to left or inside out. Okay. So what's the rule? We already wrote down. X-axis, I switch the y coordinate. Take the opposite of the y. Okay, so that's that one. Now I reflected over the line y equals x. I know that's memorized as switching the x and y coordinates. So I just switch those. So it becomes negative y comma x. There's my rule. Negative y comma x. This is what I visualize in my head and do in my head. Okay, rotation of negative 90. This is of xy. Okay, what this is this is a reflection over line y equals x following a reflection over the line over the y-axis. Okay. So remember, that's the first one. This is the second one. So what happens when I go over the y-axis? That's which is the x coordinate. Y stays the same. Now what happens when I reflect over the line y equals x? I just switch the coordinates. So now that becomes y negative x. And so there's my answer, y negative x for rotation of negative 90 degrees. On the DCAS, they will not say negative 90 degrees. They will say, instead of positive 90 degrees, they'll say counterclockwise, and this would be clockwise. Okay, so you're going to use the words clockwise. Clockwise is negative. Counterclockwise is positive. Okay, we've already written that down over here. And those are the words that they will use on the DCAS. So just know that. All right, we have rotation of 180. So I'm going 2 quadrants away. X, Y, reflection of rotation 180 is a reflection over the y-axis following a reflection over the x-axis. Or I could switch and go reflection over the x-axis following the y-axis. And so all that does is take the opposite signs of both. Okay? So rotation of 180 is negative x, negative y. Rotation of 270 is the same as a rotation of negative 90. So we've already done that. That's a rotation of 270. A rotation of negative 270 is the same as a rotation of positive 90, and we've already done that one. Okay, so we've covered everything. So this is the same as a rotation of negative 270. Okay. So there's all my rotations, and either I have to memorize just the straight rules, or as I do, as I just showed you right there, that's how I do it in my head. I know what intersecting lines they're rotating about. Remember, they're always going over intersecting lines. I memorize what the lines are, and I can then visualize what happens to x and y. But you can just straight out memorize it. All this is on your DCAS sheet. Okay, if you just want to straight memorize it. Okay. All right. Perpendicular bisector theorem. If I have a segment, this is real quick. I have a segment, and I either construct or just have the perpendicular bisector given to me. So remember, perpendicular bisector means it splits in half. This is my perpendicular bisector line L, for example. That means any point, perpendicular bisector theorem says any point on the perpendicular bisector, any point on perpendicular bisector is equidistant from the endpoints of the segment. Obviously, you can't have endpoints of a line. In this case, we call it AB, segment AB. So, real quick, what that says is if I take that point, it's on the perpendicular bisector, that distance from to that endpoint, and that distance to that endpoint is exactly the same. Or if I take that point, that distance to that distance is exactly the same. That's all it says. Okay, so that's the perpendicular bisector theorem. All right. Now we get to centroid. I told you I'd get to the centroid. Oh no, I got translation to go. And then I'll talk about dilation real quick as well. Okay, translation. Translation. X, comma, Y becomes X plus H, comma, Y plus K. Okay, so that means I've moved it. I've just added to the X coordinate and added to the Y coordinate. or subtract it, add or subtract. So if I had the rule x comma y goes to x plus 2, y minus 5, what that means is, move points on pre-image, whatever that triangle, quadrilateral is, etc., 2 to the right and 5 down. Okay, so 1 point. Let's just do it. Negative 1, 1. I'm going 2 to the right and 5 down. 2 to the right goes here and 5 down. 1, 2, 3, 4, 5 right there. So I went plus 2, and then I went down 5. So that's A. That now is A prime. Okay, that's a translation, and this is what a translation rule looks like. So if it says to write a translation rule, that means they would give you the pre-image. So here's an example of that. A, and then they give me this one right here and call it A prime. They say write a translation rule. So it's x comma y, the original point. What happened to it? How did I get from A to A prime? I went left, how many? 1, 2, 3. So it's minus 3 on the x minus 3. And how many did I go down? 1, y minus 1. That's simple. Okay, so there's a translation rule. So if you saw that, you would just do that with all the points of the triangle or quadrilateral. Okay, so it's a slide, or translation is a slide. Okay, and lastly, dilation. A dilation rule looks like this. So dilation rule. X comma y becomes ax comma a y. So I'm multiplying by the same coefficient on both the x and the y coordinates. So example, xy becomes 2x comma 2y. I can't have 2x comma 3y or 5x comma 2y. It has to be the exact same coefficient, 2x comma 2y. That's a dilation. Okay. So now we've seen all those types of rules, and they usually have a question on the DCAS. It'll give you a bunch of rules. It'll say which one is a dilation rule. You're going to pick this answer right here when it gives you 2x comma 2y. Okay, just know that. Okay, we're getting there. Almost done. Okay, regular. The word regular. Regular means equilateral and equiangular. Okay. Equilateral, remember, equal means equal, lateral means side, so equal sides, and equal angular means angles, equal angles. So regular, we're talking about regular polygons. It's always dealing with polygons. Whenever we talk about the definition of polygon, only segments that intersect only at their endpoints in a plane. So we have a triangle, quadrilateral, an equilateral triangle, a square would be the quadrilaterals one, a pentagon, hexagon, they'd all have to be congruent. So, equilateral, that's regular. It means equiangular as well. All of them have to be 60 degrees. It's an equilateral triangle. Okay, where does this come into play? When we talk about rotational symmetry. Rotational symmetry. Okay, what is rotational symmetry? It means how many degrees to rotate back onto itself. Okay. So what's the rule? It's 360 because the center, it's always rotating about the center of that regular polygon. 360 divided by n, n being the number of sides or angles, because they're the same amount, right? Usually you call it sides, but you could say angles as well. So 360 divided by 3 is 120 degrees. Every time I rotate this triangle 120 degrees, it will be right back onto itself. That's the first one. If it asks just what is the rotational symmetry singular, the answer is 120. If it asks what are the symmetries, plural, say ROT, symmetries, then I go ahead and keep adding 120 degrees. So 120 plus 120 is 240 because every 120 degrees. And if I did another one, it'd be 360, but we do not include 360. Stop before 360. Okay, so therefore, for a equilateral triangle, the only two answers are 120 and 240 degrees. But I would just keep adding on that same original one each time until I hit 360 or beyond it, and I stop the one before the 360. Okay. We also use it when we talk about finding the, if I have a regular hexagon, okay, it doesn't matter that it doesn't look like it. I'm saying it is because I have all 6 sides congruent, which means all 6 angles have to be congruent as well. So that's a regular hexagon. Okay, regular REG hexagon, 6 sides. Okay, so you might be asked on a worksheet, you'll be asked on a worksheet, or you were if you're reviewing this, find the exterior angle, the interior angle, and the sum of interior angles, meaning all together. Okay, the easiest one to do first is the exterior angle. That formula is 360 divided by n. And there's my answer. So what's n? 6. 360 divided by 6 is 60 degrees. So what that is the exterior angle. That means if I extended one of these sides out, this angle right here is 60 degrees. Well, what do I know this interior angle is? Call it to the exterior angle. Put them together and I have a linear pair. What's a linear pair? Two angles that add to 180. So it's 180 minus 60. 120 degrees. Okay. Well, so each one of these is 120 degrees. How many angles do I have there? 6. 120. I'll just put the final answer. 720. 120 degrees times the 6 angles is 720 degrees. So that's how you do exterior, interior, and sum of the interior angles. Okay, for any regular polygon. Okay. How do I know what kind of triangle I have if I'm given side lengths? So what type of triangle? And your answer is either acute, obtuse, or right. And if I'm just given the side lengths, say 10, 14, 16. Okay. The longest side is always C. And it doesn't matter which one I call the other two. So I'll just go A and B. But the longest is C. If it's acute, C squared is less than the sum of A squared plus B squared. If it's obtuse, C squared is greater than the sum of A squared plus B squared. And if it's right, it's C squared equals A squared plus B squared. And you should recognize that as the Pythagorean theorem. A squared plus B squared equals C squared. Okay, so let's go ahead and do it. 16 squared, since that's C. And I have 10 squared plus 14 squared. That's 256 if you memorize your perfect squares for extra credit. 100 plus 196 if you memorize. And so 256, how does that compare to 296? It's smaller, isn't it? So therefore, this is an acute triangle. Okay? That is how you determine based off the side lengths. It doesn't matter what the drawing looks like. I have to use the side lengths and do that calculation to check. All right, that's that one. All right, we have geometric means. We still forgot we have some big circles. Dang, we're gonna be hitting 3 hours here. I hope it saves this whole recording. Maybe I better stop right now. I'm at 225 because otherwise I'm having to start over if I really want to do this for real. So I'm going to stop right here and I'll add on in the second part.